Okay guys, today we're going to look at a position versus time graphs practice example. We've been dealing with speed and velocity, distance and displacement, and this is going to kind of tie it all together. Okay? We've been working with position versus time curves, and we know that when you have a line going up like this on a position versus time curve, you're going a constant velocity. If you have a horizontal one, we know we are stopped, right? And we know that if the slope of those position versus time graphs indicates speed, right? Okay? Or it can also indicate velocity. Okay? If we're going down a straight line track, those are the same thing. So let's look at this example. On a straight line track, Sally and her dog sled team take off from the start line at 4 meters per second. 5 minutes later, Gus and his team take off from the start line at 3 meters per second. 20 minutes into the race, Sally stops and takes a 3-minute break, then continues at 4 meters per second. 10 minutes after taking off, Gus and his team actually should go from 3 meters per second to 5 meters per second. How far down the track will Gus catch up to Sally, and how much time will have elapsed since Sally started the race? Okay, so those are the two questions that we're going to attack. For today, we're going to assume that Gus is a magic sled and he can go from 3 meters per second to 5 meters per second instantaneously. Okay, so our graphs will have nice sharp points on them instead of curves. It'll make the equations, the calculations a little easier to do. Okay, so guys, if we were to make a position versus time graph for these two people, what shape would they take in general? We're not going to get exact values here, but what shape would they look like? So let's go to Sally. She takes off and goes 4 meters per second for a while, right? And it says 20 minutes into the race, Sally stops. So she's going to go 4 meters per second for 20 minutes. Okay? So I'm going to draw something that looks something maybe like that. Right? 4 meters per second. Okay? For 20 minutes. Now, guys, what's 20 times 60? Is that 1,200? So is that going to be 1,200 seconds? Okay? So if I come down here, that's 1,200 seconds. 20 minutes is 1,200 seconds. Everybody agree? Then she's going to take a what? Sally stops and takes a 3-minute break. So 3 times 60 is what? 180 seconds? So 180 seconds, she's going to be chilling out. So 180 is that 1380 right there. Would you guys agree? Okay, and then what's she going to do? She's going to go at the same pace for the rest of the race, right? Not very straight, but you get the idea. Okay? Now, if we come with Gus, what does Gus do? 5 minutes later, Gus and his team take off. For the first 5 minutes, 5 times 60 is 300. So for the first 300 seconds, first 300 seconds, Gus does what? He's chilling at the start line, right? Then what happens to Gus? Okay, 5 minutes, Gus and his team take off, start 3 meters per second, right? And he's going to go 10 minutes after taking off. Gus and his go from 3 to 5. So for 10 minutes, he's going to be going 3 meters per second. Okay, what's 10 times 60? 600 seconds. He's going to be going 3 meters per second. So 600 seconds gets me out to what? About 900. And he's going 3, which is not going to be quite as steep. That's pretty close. Okay? And then what's he going to do? At that point, he goes from 3 to 5 meters per second for the rest of the race, right? Now, let's put some points on here. How far would he have gone, did you guys say? If he goes 3 meters per second for 600 seconds, is that 1,800 meters? You guys with me? 3 meters per second. So this is going to be 1,800. Everybody cool there? Now, really quickly, this guy was going 4 meters per second for 1,200 seconds. So how far is he going to be out here? Can we say 4,800? You guys cool with that? Okay. And then this guy, and the guy's drawing 5. This is going to be a little painful, but I'm going to do the best I can. 5. I don't know. I wish that was more linear. Let's try that again. Steeper. I don't know, something like that. You guys get the idea, right? Okay. So this slope here is 4. This slope is 3, and this slope is 5. Would you guys all agree? Okay. Now graphically, this might not be perfectly to scale, but you have the idea of what's going on the trip, right? Now, is this the point where they what? What's that say, position? That's the point that they're at the same position. Okay? So if we come across, eventually, we can hopefully find whatever that position is. And this graph is way off, I'm just going to tell you already. And then we could, if we come down here, we could find the what? The time. Everybody kind of have an idea what's going on there? If we were to draw if we were to graph this in Excel, could we get a nice, perfectly scaled graph? Okay. So, really quickly, how are we going to go about finding out what's going on here? How are we going to go about finding those 2 points, this time and that position? Well, let me propose this. If I knew this equation of that line, and I knew the equation of that line, could we go back to some algebra 2, and if we know the 2 equations, can we find where they intersect? You guys agree with on that? Okay. So if we do something like that, let's come out here and let's see how you guys, I'm pretty sure you guys are pretty smart on this. Y equals mx plus b, but we're not dealing with y, we're dealing with p, and we're not dealing with x, we're dealing with t. So could I say something like this? P equals mt plus b. Are we all good there? Okay. Now, we all know that the slope of that line is what? The speed, or the velocity, and it's 5 meters per second. So could I rewrite it like this? P equals 5 times t plus b. Pretty cool? Okay. Now, do we know a point on that line? I'm pretty sure we know what? That point? And if we know that point, I think it is point what? 900, 1800? Could we put in 1800 for the position? 900 for the time? And then end up solving for my b? What's 1800 minus 4500?
Negative 2,700.
So 2700 negative. So could I come up with an equation that looks like P equals 5t minus 2700 as the equation for that line? We good? Okay. Now this line, you guys, I think once we've done one of these, it turns out to be pretty easy. P equals mt plus b. In this case, we know our position is what? 4,800. Okay, so we could say 4,800 equals, what's the slope of that line?
4.
It's 4, right? Now, our t, what is our t going to be?
13.
Okay. Well, we knew that is it 1380 right at that point?
Yeah.
Okay. So we've drawn that in already, so we got 1380 plus b. And then b, you guys will have to help me out on that one. What's 4,800 minus 4 times 1380?
Negative 720.
Guys, did everybody, can I get a verification on negative 720?
Yeah.
Okay. So our equation looks like this for that line right there. P equals 4 times t minus 720. Are those the 2 equations for each of for this line and that line? So can we find the intersection point?
Yeah.
Okay. And we do that. Well, guys, if this equals p and that equals p, can we set this and this equal to each other?
Yep.
Okay. So I can say 4t minus 720 equals 5t minus 2700. I'm going to subtract 4t over there, which is going to leave me with nice with the t. And then I'm going to move this 2700 over there. Okay, and I think I'm going to come up with what, 1980? Is that correct? Everybody cool? Okay. So the time it's going to take from the very beginning is going to be 1980 seconds. So, how much time will have elapsed since Sally started the race? We have that answer already. Okay. Now, really quickly, how far are we going to be down the track? We just re-plug it into either of the equations, right? Okay. So if I take that t and I plug it in here, I'm going to get p equals 5 times 1980 minus 2700. And that position turns out to be, oh, I better put in a 0 right there. Anybody? I think it turns out to be 7,200. 7,200? 7,200 meters. Now guys, just for verification while I kind of talk and review, could somebody plug it into that one as well and see if we get the same thing? Okay. Now, guys, what this is kind of hopefully doing for us is we're validating the fact and reinforcing the fact that we can draw position versus time graphs. We're using the fact that we can use math and fit curves to stuff and utilize that to solve real world problems. Okay? Which I think is pretty exciting because you don't learn the math just to learn the math. You learn it, I think, to be able to solve real world problems. Okay? That's it.